Welcome. Today, we're diving into the crucial role of pressure differentials in cleanrooms. This topic is all about the first line of defense against contamination. We'll explore how controlling air pressure helps keep environments sterile and safe, a foundation for quality and precision in many industries. Let's get started. Let's talk about pressure differential, the difference in air pressure between two connected spaces. Here, we see grade B at 35 pascals, grade C at 20 pascals, so the difference is 15 pascals. Air naturally flows from the higher pressure in grade B to the lower pressure in grade C. This movement is crucial. It keeps air moving from cleaner zones to less clean ones, stopping contamination from creeping into critical areas. We measure this difference in pascals, or millimeters of water gauge. When it comes to regulatory expectations, there are some key requirements we need to keep front and center. The EU GMP Annex 1 calls for appropriate pressure cascades and continuous monitoring of critical areas. It also demands thorough investigations of any deviations and alarm systems to catch pressure excursions early. Meanwhile, WHO and PICS GMP focus on maintaining and monitoring pressure differentials, backed by solid documentation and trend analysis. The FDA's CGMP emphasizes environmental controls to prevent contamination and mix-ups. Across the board, the principle is clear. Pressure differentials must be scientifically justified and routinely verified. Let's talk about the benefits of maintaining a pressure cascade in cleanroom environments. First, it prevents contamination from entering sensitive areas. It also keeps airflow moving in one direction, from cleaner to less clean zones. This supports the cleanroom's classification and boosts overall sterility assurance. The pressure cascade means each area has a slightly lower pressure than the one before it, creating a controlled flow. For example, grade A and B rooms sit at plus 35 pascals, while corridors remain neutral at 0. This sequence is key to keeping things clean and safe. Let's talk about negative pressure rooms, spaces where the air pressure inside is lower than outside. These rooms are designed to keep potent compounds, cytotoxic products, and biological hazards contained. The goal is to protect both the people working inside and the environment beyond. On the flip side, positive pressure rooms have higher pressure inside to keep contaminants out. Think of sterile manufacturing or aseptic filling. Like an aseptic filling room that might be 35 pascals above the surrounding area, ensuring the product stays pure. In cleanroom environments, maintaining proper pressure differentials is crucial. Most facilities keep at least a 10 pascal difference between adjacent cleanroom grades. For example, if grade B is at 30 pascals and grade C at 18 pascals, the difference is 12 pascals, enough to ensure airflow moves in the right direction. This helps prevent contamination by pushing air from cleaner to less clean areas. Typical transitions, like from grade B to C or from a cleanroom to a corridor, usually require between 10 and 15 pascals to maintain this controlled airflow. Let's talk about airflow and contamination control and how pressure plays a crucial role. Air always moves from areas of higher pressure to lower pressure. This simple fact helps us keep contaminants out. By maintaining the right pressure differences, we prevent airborne particles from entering sensitive spaces, reduce the movement of microbes, and protect exposed products. For example, when a door to a grade C room opens, air flows outward into the corridor, stopping contaminated air from coming in. It's a smart, effective way to support aseptic conditions. Let's talk about monitoring systems, the tools and methods we use to keep an eye on important conditions. Instruments like magnehelic gauges and differential pressure transmitters give us precise readings. These connect to larger networks, such as building management systems or SCADA systems, for real-time oversight. Monitoring comes in two forms: continuous, for critical areas where constant data is key, and periodic, for lower-risk zones checked less often. For example, in a grade B area, pressure is monitored every 60 seconds and recorded electronically to ensure safety and compliance. Let's walk through a simple example of calculating pressure differential between two areas. Here, we have a grade B area at 32 pascals and a grade C area at 20 pascals. The formula is straightforward. Subtract the lower pressure from the higher one. So 32 minus 20 gives us 12 pascals. Since the required minimum is 10 pascals and 12 is greater than 10, this passes. The pressure cascade is maintained as it should be. Let's talk about pressure excursions and how they affect risk. When pressure drops or reverses, it can cause airflow to go the wrong way, letting particles and microbes in. That risks contamination and compromises sterility. When this happens, we investigate the deviation and assess how the product might be impacted. Then, we put corrective actions in place. For example, if the specification calls for a pressure of plus 35 with a margin of 5, but we observe only plus 18, we need to find out why. It could be HVAC issues, a door left open, HEPA filter blockage, or a damper failure. Let's talk about how modern alarm systems are stepping up with automated pressure monitoring. These systems keep an eye on pressure in real time, alerting us visually and audibly the moment something's off. They even send SMS or email alerts, so we're always in the loop. On top of that, trend analysis helps us spot patterns before problems escalate. The real game changer, AI-based predictive monitoring. It can forecast HVAC failures, pressure drifts, and filter loading, like predicting a pressure drop hours before it happens, giving us time to fix things before they go wrong. When we control pressure properly, the benefits ripple across the entire operation. First, it protects the product by reducing contamination risks and boosting sterility assurance. Operationally, it keeps environmental conditions stable and cuts down on deviations. From a compliance standpoint, it means we're always ready for inspections and meeting GMP standards. This includes having qualified HVAC systems, clear pressure strategies, continuous monitoring, and robust alarm and data management. All these elements work together to maintain integrity and meet regulatory expectations. Pressure differential is our first and most critical defense against contamination in pharmaceutical cleanrooms. By carefully controlling airflow from cleaner to less clean areas, we stop particles and microbes from sneaking in and compromising product quality. This requires a well-designed pressure cascade, continuous monitoring, and integration into the overall contamination control strategy. When done right, it keeps the cleanroom environment stable, supports compliance with global standards, and ensures the safe production of high-quality medicines. Thanks for joining me today. If you want to explore this topic further or have any questions, please don't hesitate to reach out. I appreciate your time and attention, and I look forward to continuing the conversation. Thank you. This video was created with SlideSpeak. Visit SlideSpeak to turn your presentations into engaging AI-narrated videos.